All right, we have a simple harmonic motion problem here. And I'm actually going to start by reminding us about the simple harmonic motion equation. So the equation of motion for us, which is, let's just remind us ourselves of that. X of t, this is the general equation, equals a cosine omega t plus phi. And if you haven't done the oscillatory functions review, stop right now. Go back and do that review first. It's really hard to kind of figure out where you are with this function unless you're right on top of the function form. So please do that first. All right, so the reason that I bring up the equation is because I want us to be able to kind of parse out this example that we're given here. And in this example, there are some interesting things about it, but I write it this way on purpose because they're often given like this. So the amplitude term, if I look at my example here, I can see right away that, okay, I can just upon inspection see that the amplitude of my function is 5 centimeters. That's given right in there. And I can also see that the angular frequency is, now note, there are no units on that 2. It's just written as 2t plus pi over 6, right? But I know there must be units on the 2 because I know that the quantity in parens there, the argument of the cosine function, I know that has to be in radians, right? So that kind of tells me that, oh, right, what that must be there is radians per second. Oh, 2 radians per second. And that's just given as a 2 with that 1 sig fig there. So I'm just going to write it that same way. And then my phase shift there is given as pi over 6. Good. And again, if any of this is like, what's the phase shift? What does that mean? Go back to the oscillatory functions review because that's all covered in that assignment right there. Okay, so um, here are the quantities, the pertinent quantities that I can extract just from looking at my equation. Great. So at t equals 0, notice that this problem is asking us to find some things at t equals 0, right? So at t equals 0, I want to determine what the displacement of the particle is. All right. So the displacement, I have the displacement function. The displacement at t equals 0 is going to be equal to 5 centimeters times cosine 0 plus pi over 6, right? If I sub this in, what I get is something like 4.33 centimeters. Okay, so there's displacement at 0, at t equals 0. Now this part B asks me for the velocity at t equals 0. So how do I get the velocity function? Well, the velocity function is, of course, just the first derivative of my position function. And in this particular problem, my position function is given, right? So I can figure out what my velocity function must look like. So my velocity function in general, it's just going to be the first derivative of my position function. So that will be equal to negative 2 radians per second times 5 centimeters times the sine of 2t plus pi over 6. Great. Now this particular problem is asking me to find the velocity at t equals 0. So now I can do that. The velocity I'll write it like this to make it a little more clear. At t equals 0, it's going to be equal to, I still have my 2 radians per second, 5 centimeters times sine of 0 plus pi over 6. When I sub that all in, I get negative 5 centimeters per second. So I want you to notice something. So we got, for at t equals 0, our position right, is positive. So we're positive displacement from the equilibrium there. Our velocity is negative. So our velocity has the opposite direction from our position. I just want you to kind of wrap your mind around that. And remember, you're thinking about something that's oscillating. So it's a piston that's oscillating back and forth. Okay. Um, C asks for its acceleration at t equals 0. So we're going to do all those same things. The acceleration function is the first derivative of the velocity function with respect to time. So that'll give me negative 2 radians per second squared times 5 centimeters times, again, going back to the cosine function, right? Cosine of 2t plus pi over 6. So that's my general equation. If I sub that in for t equals 0 there, which they're asking me to do, what I'll get is acceleration at t equals 0 will be equal to negative 17.3 centimeters per second squared. So notice right away that the velocity and acceleration both have the same sign. When they have the same sign, you know the particle's doing what? Think about it. That means the particle must be speeding up, right? When velocity and acceleration have the same sign, you have a speeding up body or particle. When they have opposite signs, then you know that the particle is slowing down. We learned that really early on in 221, and that still applies here. So it can help you wrap your head around, like, what is the particle doing? Try to not just go into math mode when you're doing these simple harmonic motion equations. That will not allow you to actually learn what you need to learn about it. But really try to stay physical and think about, like, where is the particle and what is it doing? So this would be, like, for instance, a particle that has a positive displacement. You could, let's see. So here is x equals 0. Say there's my equilibrium point. And say I have positive x going to the right and negative to the left. Then I could say this would be like the particle is, where is it, right? It's here at positive 4.33 centimeters, but its velocity and acceleration are both directed to the left, and it's speeding up to the left. So what that means is that, to me, is that it's on its way back to equilibrium. At equilibrium is where it's going to be going the fastest, right? So it makes sense that it would be speeding up if it's on its way back to equilibrium. So at the very least, try to stay in touch with, where is it? Is it speeding up or slowing down? Is it on its way back to equilibrium, or is it on its way out to the maximum displacement, otherwise known as the amplitude? Okay, so again, this problem is just really to kind of help you wrap your head around interpreting one of these equations. So we've solved for all this stuff. Part D asks us to determine the period and the amplitude of the motion. We've got the amplitude. We could read that right off of the equation itself. And then to find the period, well, we have the angular frequency here, and I know that period is equal to 2 pi over the angular frequency. So I end up with, for period, if I sub in what I'm given, my 2 radians per second, then I'll be given that that's equal actually to pi seconds. So I have solved for that part too. Okay, so big lesson here is when you're doing these simple harmonic motion problems, even if you're able to sort of crank through the equations and substitute in the stuff and get where you're supposed to get, do your best to still, even if you just draw a really simple diagram like the one I drew, where is this particle? And notice there's something else I want you to notice about this problem actually. Notice that this is a weird place for t equals 0 to be, right? There's nothing special about this spot. It's not at equilibrium. It's not at x equals a. It's at a random point in the motion that t equals 0 is. There's nothing special about it. Now, we didn't control that because we didn't control this function, right? We were just handed this function. So I want you to remember that t equals 0 when you can choose your function, you're allowed to choose when the clock starts. That's all that t equals 0 is, and it has an effect on your, that's what you use your phase shift for, right? Is essentially where you decide to start the clock. Sometimes in problems, you're allowed to choose that. You can completely write your own equation. Other times in a problem like this, it's chosen for you. So be careful about having any kind of expectations about what the system should be doing at t equals 0.